Have you ever stopped to think about what happens when you flip a light switch or open your fridge? You are tapping into a silent, invisible army of machines. And today, we're going to pull back the curtain on the 3 electrical workhorses that, no exaggeration, make our entire modern world possible.
Right, so let's get into it. We all know electricity is everywhere. We take it completely for granted. But just making the stuff is only half the battle. The real puzzle, the thing that kicked off the modern age, was figuring out how to tame it, how to move it hundreds of miles, and then how to make it actually do something useful.
And really, it all boiled down to 2 massive but totally different problems. First, how in the world do you get all that power from a distant power plant all the way to a city? And second, once you've got it there, how do you turn that invisible energy into actual physical movement?
And this right here lays out the 2 sides of that coin perfectly. On one side, you've got the logistics problem, just moving the power without it fizzling out. On the other side, you've got the conversion problem, turning that power into force. And solving these 2 things required 2 very different but equally brilliant kinds of machines. So let's tackle that first challenge, moving power. The hero of this part of the story is a device that's kind of strange because it has no moving parts at all. But without it, our power grid simply wouldn't exist. I'm talking about the transformer.
Now, the key thing you got to get about a transformer is that it doesn't create power. It just changes its form. The best way to think about it is like a gearbox for electricity. You know how a car's gearbox trades speed for torque? Well, a transformer trades voltage for current. And that simple trade-off is absolutely fundamental to making the whole grid work. So how does this thing even work? Well, the secret sauce is something called mutual induction. You run an alternating current through the first coil of wire, and that creates this pulsing magnetic field. The iron core then guides that field over to a second coil, and, this is the crazy part, with no physical connection, it magically creates a brand new current over there. It really does feel like magic, but it's just pure physics.
And this is exactly why it's so critical. To send power over those super long distances, use a step-up transformer to crank the voltage way, way up. This cuts down on energy loss. But you obviously can't have 1,000,000 volts coming into your house. So near your home, a step-down transformer takes that super high voltage and drops it to a safe, usable level. It's this 2-step dance that makes the whole system work.
Okay, so the transformer solved problem number 1, moving power. Awesome. But now for the second big challenge. How do you make stuff actually move? Well, that brings us to the OG, the machine that first turned electricity into motion, the direct current, or DC motor.
This is it. This one simple, beautiful law of physics is the secret behind every single DC motor. You just run a current through a coil of wire that's sitting inside a magnetic field, and that creates a force, a push, and that push makes the coil spin. That is the fundamental trick for turning electricity into work.
But here is where it gets truly genius. As that motor is spinning, it also starts acting like a tiny generator, and it creates a reverse voltage called back EMF. This back EMF literally pushes back against the current coming in. So if the motor's load is light and it speeds up, the back EMF goes up and less current flows in. If the load gets heavy and it slows down, the back EMF drops, which lets more current in to give it more muscle. It's this beautiful, self-regulating system.
And just by changing how you wire up the coils inside, you get completely different behaviors. A series motor, for example, it's got this thick wire winding that gives it a massive burst of power right at the start. Incredible starting torque. That's perfect for things like cranes. But a shunt motor, with its wiring in parallel, is designed to just hold a nice, steady speed, which is exactly what you want for something like a fan or a pump.
Now, the DC motor was a game changer, for sure, but it had these little parts called brushes that would wear out. So the next great leap forward was a motor that was way simpler, tougher, and needed almost zero maintenance, the AC induction motor.
And what's so revolutionary here is that there is no physical contact to make the rotor spin. It's wild. An induction motor uses that same magic we saw in the transformer. Induction. A rotating magnetic field in the outer part induces a current in the inner part, the rotor. And then the rotor basically just gets dragged along for the ride.
This brings us to this really weird but absolutely essential idea called slip. See, for the motor to actually work and create torque, the rotor can never quite catch up to the speed of the rotating magnetic field. It always has to be slipping just a little bit behind it. That tiny difference in speed is what makes the whole induction thing happen. It's kind of funny. It has to always be losing the race in order to win it.
And we're talking about a tiny, tiny difference. For a typical motor, the slip might only be about 2%. Just look at this example.
The magnetic field is spinning at 900 RPM, but the rotor itself is turning just behind it at 8080. All of the power, all of the force of that entire motor is generated in that little 2.22% gap. I mean, that's just incredible.
So when you put them side by side, you can really see the evolution. The DC motor is brilliant, but it's also a bit complex. The induction motor, it's just elegantly simple and incredibly tough. And that is why induction motors, especially what's called the squirrel cage type, became the absolute workhorses of modern industry. They just run and run and run.
So, okay, let's pull all this together. You've got the transformer to move the power, and you've got the DC or induction motor to turn that power into motion. These aren't just some abstract ideas from a textbook. They're the literal physical foundation of the world we live in.
I mean, just think about it for a second. The entire power grid, that's transformers. Electric trains, giant cranes, they're using the raw power of series DC motors. Your AC unit, your fridge, nearly every machine in a factory, they're all running on tireless induction motors. Even your vacuum cleaner probably has a zippy little series DC motor inside. They are, quite literally, everywhere.
These three machines form this invisible, interconnected system. Power gets stepped up by a transformer, travels across the country, gets stepped down by another one, and then gets fed into a motor that spins a fan or runs a compressor in your home. They are the true unsung mechanical heroes of the last century.
And that leaves us with one last thing to think about. We are diving headfirst into this new age of electrification, right? With electric vehicles, smart grids. The principles we talked about today are timeless, but the technology is always changing. So what do you think the next revolutionary electrical machine is going to be? Thanks for watching.